In today's lecture, we will start looking at some of the properties of marginals, which lead to one of deep concepts in calculus, namely convexity and concavity. So, before introducing that concept, let us look at the scenario in mathematically. Let x represent a single input that is used to produce an output y. That means, y is a function of x and the functional relationship is represented as y equal to f of x. So, x is the input and y is the output of some quantity, whatever it may be. So, we will later on see examples to illustrate this. So, in that case, we the product function, the production function is given by this is what is called the production function, right. Okay, fine. So, now look at the derivative of this. So, if this is called the product function or the production function, so marginal of the product will be the derivative of this function. So, marginal m p of x is the marginal and that is equal to f dash of x, that is the derivative of the function f of the product function or the production function. Now, one would like to know if the marginal is increasing, if the marginal is a function of x, again it is a derivative of the we have assumed that the function f is differentiable everywhere. So, derivative is again a function. So, marginal is a function of the input x again. So, if the marginal is decreasing, right, if this marginal is decreasing as input is increasing, called the law of diminishing marginal product, that is f is decreasing, right, implies the derivative of that, okay, derivative of f dash should be less than 0. Okay. So, that is what so the point we am trying to make is that saying something about the marginal is revealed about the property of the second derivative of the marginal of the function, product function. So, that is the second derivative. So, this we want to study mathematically more deeply. So, what we do is the following. Similarly, marginal is increasing. If the marginal is increasing, right, that means the input is increasing. Okay. If the marginal is increasing, that means here there is a mistake, input is decreasing. So, if the marginal is increasing as output is increasing, then f dash is an increasing function and that means what, f double dash must be bigger than 0. So, all this we want to make it mathematically very precise. So, let us look at mathematically what this means. Of course, the second scenario in economics does not seem to be a plausible situation, where it says that the marginal is increasing as output is increasing. So, that does not seem to be a very good situation in economics. So, let us come back to mathematics and then see how do we imply. So, for example, if in economics, for example, if all other inputs are fixed and if x represents, for example, labor, then it is not true that increase in labor will give you increase in marginal, that is greater in increments in output. That may not always happen, that we know. So, that is why this scenario may not always happen, right. So, let us continue with our examples of monopoly market that we have been looking at. So, we have looked at an example of a monopoly firm with the demand price function P q equal to 10 and cost function as C q equal to 5 q. For this, we wrote down the various functions P equal to 10 q minus 1. So, here P q was 10. So, q on the other side if you take it, so you get price demand relationship P is equal to 10 q minus 1. The revenue function is P q. So, that comes out to be multiplication is equal to 10, that is a constant function. And then you look at the profit function, the revenue function minus the cost function, that comes out 10 minus 5 q. So, we had done this, I am just revising it. So, we observed that the output is reduced, the price rises, but the revenue remains unchanged. So, in this example, this is what the observation we had made, the output is reduced, then the prices rise. If the output is reduced because it is 1 over q, so if output is reduced, the price will go up, but the revenue remains constant. So, now it pays to reduce output. It is not really, it cannot be done, because you cannot reduce output as much as you like. You cannot make it a fractional kind of a thing. So, in reality this scenario is not really useful. That is what we had observed, and for this model we had computed the coefficient of elasticity, which came out to be 1. So, coefficient of elasticity, this is a unit coefficient of elasticity example. So, let us look at one more example. So, consider the variation of this example, namely consider a firm with demand price as p square q equal to 1 and the cost function as cq equal to 2q. So, here the cost price function, demand price function is given by this. So, if you want to write p as a function of q, then p square is equal to 1 over q. So, p will be equal to square root of 1 over q. So, that we can do. So, we can write p as a function of q to be q square root of q. So, we have written it as q raised to power minus 1 by 2. Okay. So, the revenue function is p into q. So, this is p and into q. So, that gives you q raised to power half into q raised to power 1. So, total power becomes q raised to power half, and the profit function is given by RQ minus CQ. So, RQ is here q raised to power half and CQ is equal to 2q. So, when you put that values, you get the profit function to be equal to q raised to power half minus 2q. So, all the basic functions are there. So, now we can observe that reducing the output, if you reduce the output, see q is equal to q raised to power half. So, this is a increasing function as such. So, if you increase the output, RQ will go up. So, reducing the output, if you other way around, if you reduce the output, then the revenue is also reduced. But you can do it only when till q remains a positive value. So, that means if you increase q, then RQ is going to increase, and if you reduce q, then the revenue is going to decrease. So, profit is going to increase. So, at some positive value, the maximum profit can occur. So, that is the this model says that positive at some positive maximum profit at some positive value will occur. So, graphically let us plot these two functions. P is equal to 10q minus 2. So, PQ is not 10, it is just q raised to power minus 2, and MCQ is equal to 2. So, let us plot this. So, this is the this blue one is the revenue function, which was equal to q raised to power half. So, that is a revenue function, and the cost function is C2q, that is a cost function, that is a linear function. So, that is it, and pi q, the profit function, is q raised to power half minus 2q, and that is the graph of it. So, if you look at the graph, as the production increases, it keeps on increasing and then it starts decreasing after some point onwards. So, the profit occurs at the value when d is equal to 0.6. Not a very realistic situation, but still from the graph that is what we get. So, if you want to verify it mathematically, we will look at the derivative of the profit function. So, that is equal to this, right. Recall the derivative pi was equal to this. So, derivative of this will be half q raised to power half minus 1 into 2 minus 2, derivative of 2q is 2. So, we can put this value in the derivative function. So, we get the derivative equal to this. So, which if you want to maximize this, we have to put derivative equal to 0 to look for the possible values. So, when you put it equal to 0, q comes out to be 1 over 16 from this equation. So, 2 into 2 4. So, q raised to power half is equal to 4. So, q will be equal to 1 over 16. So, that is approximately 0.6. So, that is a point where possibly the maximum value can occur. One can verify it by the second derivative test if you like, or you can check it from the first derivative. So, we leave it for you to check that this point is a point of absolute maximum for the function. So, that is how you will verify it mathematically from this. What is visible from the graph can be verified mathematically. So, let us calculate the coefficient of elasticity coefficient of elasticity of demand for this function. So, that comes out to be by formula it is dq by dp into p by q. So, put the values and simplify, that comes out to be equal to 2. So, again this is an example of a constant demand constant coefficient of elasticity of demand, that is 2, which is bigger than 1, and in this model the profit is maximized at some point, okay, though not very realistic. So, that is the mathematical way of saying things and what they imply in terms of economics. So, again the coefficient of elasticity is constant, but it is bigger than 1. Okay. So, let us look at just recalling then in the example of unit elasticity that we had discussed in the previous lecture, and we have revised today also in the beginning. Profit could be increased as much needed theoretically. So, there we said that if you make output smaller and smaller, the profit keeps on increasing, but that is only theory. In practice, you cannot make the production how much you produce to be very, very small. So, but that was unit elasticity scenario. In the present case, we have again the coefficient of elasticity is constant, but the value is equal to 2, it is more than 1, and in this case reducing output reduces total revenue. So, that means if you increase the output, you will increase the revenue, and a positive value of output exists giving the maximum profit, and that is what we observed happened at the point q equal to 0.6. So, we are relating the coefficient of elasticity with the existence of profit, maximum profit, and so on. So, this is the comparison of the two scenarios. Let us consider one more example still, namely consider a firm with the demand function to be equal to p raised to power minus half and the cost function to be equal to 2q. So, with this scenario, let us write down the functions. So, if you q is equal to p raised to power minus half, so if you take it on the other side, p raised to power half will be equal to 1 over q. So, when you square both sides, you will get the relation p is equal to 2q, p is equal to q raised to power minus 2. So, that is the relation between the price and the quantity being produced. Once again note that this q to the power minus 2 means it is equal to 1 over 2 to the power q, 1 over q square. So, as q decreases, p is going to increase. So, once again the decrease in cost, decrease in the quantity produced increases the price. Okay. So, so this is what we call as a inverse demand function. Okay. So, the revenue function for this will be equal to p into q as usual, price into the quantities being produced. P is equal to q raised to power minus 2 into q. So, that becomes revenue is equal to q raised to power minus 1. Okay. So, if we look at the derivative of this revenue function, that is q raised to power minus 1, its derivative will be minus 1 into q raised to power minus 1 minus 1. So, that is equal to minus q minus 2, minus of q raised to power minus 2. So, whatever be q, it is 1 over q square. So, that is going to be negative. So, that means what? So, the derivative of a function being negative, the function is going to be a decreasing function. So, revenues will rise as q falls. Okay. So, this is going to be a decreasing function. So, because is 1 over q, right, or q. So, this one we are deducing it from here, look at it. So, revenue is equal to 1 over q. So, if q falls, that means what? Q becomes smaller, 1 over Q is going to become bigger. So, revenues will rise as Q falls. So, that is a conclusion from this equation. Okay. This only says that it is a decreasing function. Okay. So, the marginal of cost is equal to 2, that means implying that cost will also fall as Q falls. Okay. So, that is positive, right. So, a firm can increase profit by reducing output as long as Q remains positive. So, profit can be increased by reducing Q. So, that is what the outcome of this says. So, let us look at the various graphs, we can plot them. So, for this, this is C Q, that is a linear function. So, that is the straight line. The demand function is P equal to Q raised to power minus 2, that is a green one. So, this is the green function. So, this is the function which is Q raised to power minus 2, and the blue one is the revenue function, that is Q raised to power minus 1. Okay. So, the profit function is pi Q. So, that is Q raised to power minus 1 minus 2 Q. So, that is this graph, that is the profit function. So, these are the various functions related with the economic scenario, which help us to say a few things. For this model, the coefficient of elasticity is 1 by 2, which is less than 1. So, that is that one can compute, and we will do that and see that it comes out to be equal to 1 by 2. So, here there is a nice observation here, that if you look at this green graph, the green is the demand function, okay, and the blue one is the revenue, they intersect here. So, what does that intersection mean? That means at this point the quantity produced, that price is equal to the revenue. So, that will be the conclusion of this. There are various other interpretations one can make, that depending upon what you are looking at. Let us look at one more example for our scenario, and that is as follows. Consider a book publishing house that pays the author a royalty of 15%. So, when you publish a book, the publisher prints the book, sells the books, and then the author is given a part of the selling price of the book as the profit, as the royalty. So, this publisher is offering author a royalty of 15%. The demand for the book, the demand function for the book is given by 200 minus 5p, right, and the production cost for the publisher to produce the book is given by 10 plus 2q plus the q square. This has been a typo here, this is a small q, but that is same as notation is q, that is the quantity is being produced, right. So, it is 2q plus q square. Okay. So, this scenario being given, what is it one is interested in? The author would like that there should be maximum possible profit for him from the royalties. That means he would like to know the number of books that should be sold by the publisher, so that it profit is maximized. On the other hand, the publisher would like to know what is the optimal scenario where his revenues will be, his profit will be maximized. So, this is profit of the publisher versus the royalty of the author. So, we would like to know this. So, find the optimal sales from both the publishers and the author's perspective. So, we would like to know from author's point of view and publisher's point of view how much the author thinks the publisher should be selling, so that his share of royalties is maximum, and on the other hand the author would like to know how much he should sell, how many books he should sell, so that his profit is maximum, because he has to produce the books, he has to spend on the cost, he has to give a royalty and so on. So, let us try to solve these two problems. The first, the Q is 200 minus 5 p, right. So, that gives you p in terms of q as 5 p is equal to 200 minus q, there is something 5 p is equal to 200 by q. So, that is, so let us see what is the typo here. So, here 5 p goes that side is equal to 200 minus q, right. So, that is 200 minus q. So, that means dividing by 5, that is 4 minus 1 by 4 q. So, that should be 1 by 4 q, and so there is a typo here. Okay. So, let us see if that is corrected. Yeah. So, that is 40 minus. So, this part is extra here, 0.2 q, that is there. That part is okay. So, this typo, that minus 40 is extra term here. From this equation, p is equal to 40 minus 0.2 q, right. Okay, well, divide by 5. So, author's income will be given by, so 15% of the royalty, right. So, again it should be 15 by 100 here, not 10. So, this should be 15 by 100 here, 15 by 100 into p, so that is selling price. So, that is his profit, and q units are sold. So, that will be his royalty of the author. Okay. So, once you do that, so that is 0.15 and 0.15 of p into q. So, p is 40 minus 0.2 q into q, and q, the value of q is equal to 200 minus into q itself, right. So, when you simplify this equation, you will get 6 q minus 0.03 q square. So, simple calculation will tell you this is, so modulo this typo here, it should have been 100 here, and once you simplify it should come out to be this. So, what we want to do is optimize this function, which is 6 q minus 0.03 q square. So, to maximize that, we look at the derivative. So, that will be 6 minus 2 comes down, so 0.06 q. And to find out the possible point where it can have a maximum, we have to put it equal to 0. So, this equation gives you q equal to 100. So, at q equal to 100, possibly the maximum of the revenue of the author will be there when there is sale of 100 books. How do you know this is the maximum, point of maxima? Well, one can differentiate this again if you like. So, double dash second derivative of this function will be minus of 0.06, and that is a negative quantity. So, if the derivative is negative at a point, actually it is a negative constant everywhere. So, the point of critical point should be a maximum. So, q is equal to 100 is the optimal which the author can hope that if the publisher sells 100 books, he will make his profit or his revenue or his royalty will be maximum. So, let us call this as QA to be equal to 100. Let us look at from the point of view of the publisher, the profit of the publisher will be RQ minus CQ, right, minus the royalties he has to pay to the author. So, now normally the profit is RQ minus CQ, but here he is also incurring a running expenditure depending on how many books he sells. He has to give a profit, he has to give 15% of royalty to the. So, that means RQ is minus CQ minus RAQ. So, let us put the value. RQ is PQ, CQ is here there is a typo again here, it should have been Q instead of X is Q square. So, 10 plus 2Q plus Q square minus RAQ, we got it 6Q minus 0.03 Q square. So, in this calculation, please treat X as capital Q. Okay. So, once you do that and you simplify this equation, so this comes out to be 32 minus Q minus 1.32 Q's. So, it is not Qx square, it is Q square. So, X is extra here minus 10. So, I am sorry for the typos here. So, that comes out to be equal to this. So, when you to optimize the profit function, so there is no x here, it is q square. So, once you want to maximize this, you have to differentiate 32 q, derivative will be 32, 1.32 q square will give you 2 times 1.32, that is 2.46, and q, and that equal to 0 gives you the value maximum profit being q. Anyway, modulo this minor arithmetical typos, you will find out by the derivative test. First derivative equal to 0, find the derivative of the profit. Here the only thing to be noted is profit is RQ minus CQ, the revenue minus the cost. So, revenue is PQ, cost function is given, minus the revenue of the author, that has to be subtracted from to find out the profit. So, it gives you q equal to partial derivative to be the derivative, first derivative equal to 13. So, that means that possibly the maximum can occur at the point of 13. Once again, if you take the second derivative, that comes out to be negative. So, this is the point of maximum for the function pi q also. So, as far as author is concerned, the publisher should be selling 100 books, while the publisher to maximize his revenue thinks he should be selling only 13 books. So, there is a conflict of interest between the two. So, the publisher would like to sell lesser number of books to maximize his profit, whether right, lesser number of books than the author thinks. So, this is a comparative statement we can get from. So, all this analysis uses the properties of derivative and its applications. One can look at the graphical representation of this, and that is nothing but saying that you look at this is the publisher's profit function, this red one, and the green one is author's revenue function. So, that maximizes at the point of 100. So, when 100 books are sold, author's profit is author's royalty is maximum, and when it is only 13, then the publisher's profit is maximum. And here is an interesting scenario that graphically these two intersect at the point G. So, G is the value which will give you equal amount of profit for the publisher as well as the author. So, both will have same amount of take home, or whatever we want to, the publisher's profit will be equal to the royalty, but that rarely happens. Always publishers would like to make more money on the sale of books than the author can get. So, this is how we will use the calculus and its derivatives, properties of the calculus to maximize or minimize the problems. So, let me just have a recap of what we have been doing till now. Namely, we looked at the scenario of how calculus is used in optimization problems. We looked at increasing, decreasing of functions. We looked at the critical points in terms of the derivative. We had the condition in the beginning that if a function has a local maxima or a local minima at a point, and if the function is differentiable at that point, the derivative must be equal to 0. So, this is a crucial theorem that helps you to locate the possible points where the function can have a extremal value. So, given a function and look at the domain of the function, see if there are any endpoints in the domain of the function, look at the points where the function is not differentiable and the points are interior, or look at the interior points where the derivative is equal to 0. So, that gives you the possible points where the function can have extremal values, the maxima or the minima. To analyze which of them is a maxima, which of them is a minima, you have to apply various tests. You can apply the continuity test, you can apply the first derivative test, or you can apply the second derivative test. So, in all these tests, please be sure that the conditions are satisfied, because for the first derivative test, for the first continuity test, the function should be continuous, and if it is continuous at that point and it is increasing on the left, decreasing on the right, then it will be a local maximum and other way around. For the first derivative test, we do not need the function to be differentiable at that point, we only need that on the left side the derivative should be say positive, on the right side of the function point the derivative is negative, then there will be a point of local maximum and similarly for local minimum. And the second derivative test is that once you have located a point where possibly it can have a local maxima or minima, if the function has second derivative at that point and it is bigger than 0, then it is a point of local minimum, and if it is less than 0, it is a local maximum. And these critical points also help you to analyze absolute maxima and absolute minima of a function. The only condition is that you should ensure that absolute maximum and the absolute minimum exist. So, out of all the critical points, look at the points where the largest value of the function takes place and the smallest value takes place. So, you will locate the points of absolute maxima and minima. So, this is how calculus tools are used to locate optimal solutions or optimizations. We will continue with our study of applications of calculus tools in some finer aspects of analyzing functions in the next lecture. Thank you.